Hi, everybody. Let's see, slightly off here. Hold on. There you go. Today, this is the second of two lectures for asynchronous presentation for Tuesday, June 9th. And I want to talk about an example problem, which I'm calling a train of blocks. So this is a problem where we think about, start to think more carefully about systems. So here's how I set up the problem. I've got a surface up here, so this is frictionless. And on the surface, I'm going to put a bunch of blocks. And every block, let me use colored block. Every block will be identical, which is to say that each block has its own mass. So I end up with n blocks each of the same mass. And I'm going to label the blocks in a consistent way. So I'll call this block block 1, block 2, block 3, block 4, and this will be block n. So in here, there could be one more block. Here I've got 6 blocks, but there could be 10 blocks or 50 blocks, whatever your favorite number is, okay? Lots of blocks, all the same mass. And then I'm going to connect each block with a piece of ideal string. And I'm going to use a labeling scheme so that each piece of string has a tension on it, an unknown tension, that corresponds to the numerical value associated with the block to its left. So I'm going to call the tension on this particular piece of string T1. I'm going to call the tension on this particular piece of string T2. And this will be T3, and so on and so forth. And then finally, I'm going to take this whole system and I'm going to apply an external force to it, which is given, which I'll call F sub f. Sorry, you can't quite see that. It's slightly out of the page here. So there we are. So that's the problem. And let's just think intuitively about what we think is going to happen. So again, I always advise people before you start in, run the movie and ask yourself what you think is going to happen in your head. You've got all these blocks together. They're on a frictionless surface. And you apply a horizontal force. So that's going to start pulling on this block, which of course will then start pulling on all the other blocks together. So it's a train in the sense that as I start to pull, the tensions come on. And if I'm pulling with a constant force on this whole system, I expect them to all the blocks to accelerate in the same direction. So every block, I don't know what the acceleration is, but every block in the system will basically move with the acceleration. I don't know it, but I know that the acceleration of block 1, block 2, block 3, block 4, block 5, they'll all be together. That's a kinematic constraint, that they all have the same acceleration. Anytime I hook up bodies with a piece of string, an ideal piece of string, that puts a kinematic constraint on their motion. In this case, it's a very simple constraint that they all move together and therefore they all have the same acceleration. So I'd like a general philosophy. What I'm looking for now is a way of calculating that acceleration. And I'm also looking for a way of calculating each of these individual tensions, no matter how many tensions I have. It would be nice if I could write down in a way that is some sense of the word independent of the number of blocks. In other words, I could imagine that some arbitrary string, I could say that if this is the first and the second and third, this would be the ith string. Let me label that in. So if I've got, if this is the ith block, I've got an ith piece of string. So one approach is I can write a generic free body diagram for the ith block. So free body diagram for the ith block, I out of n. So 1, 2, 3, 4, dot, 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 I, dot, 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 n, whatever you're going to have. And there are vertical forces, but because they don't come into play in determining any of these other things, I'm just going to sketch them in and then ignore them. the key issue is what about the tensions? So there's in between any, the first block is special and the last block is special, but the ith block will have two tensions on it, one of which I label T sub I, that's on the right side, and then the other side, assuming it's not block 1, it'll be T sub I minus 1. And this works fine even for the first and the last block because I could define the T0 tension as 0, and I could define the Tn solution as, well, not that, but just replace it with FF, right? And then I've got every free body diagram. And again, the only coordinate I care about is the coordinate of motion of the system, which I'll call X. And in principle, the way to solve this problem is I write down N of these free body diagrams. So, the first, the second, the third, I write them all down. I write down F equals MA for all of them. Each F equals MA will have two T's and an A. So I end up with A plus, well, again, one of those is 0, so that's easy to figure out. But I end up with, and an F of app with N, so I end up with N equations and N unknowns, where N is, the unknowns are Ti through Ti minus 1 plus A. So N equations and N unknowns. And then I can solve that problem. That could be tedious, especially if you've got 50 boxes. So I'm looking for a shortcut. So the first shortcut is the obvious one, which is that I can get the acceleration quickly if I treat the whole thing as a single system. So, so the first thing I can do is I can define a system, which is basically M_sys equals M1, M1, M2, all the way, basically all the way up to M sub N. But of course, that, the mass of that system is just, well, every block is the same mass. So the mass of this system is just equal to the number of blocks, N, times the mass itself, right? That's given. Each system is given and N is given. So I know the mass of the system. And then I can do the free body diagram of that system. So here's the free body diagram of the system as a whole. And it's very simple free body diagram. Again, vertical forces, we don't care. The only force on the system, again, I treat all these bodies. I can ignore all these tensions because those tensions are inside the system. Right? I put a boundary around all those, the system includes the pieces of rope, so I don't have to worry about the tension between the individual things. So another way to think of this is each one of these tensions inside, if there's a force applied to block 3, there's an opposite force applied to block 2. So they all cancel out by the third law anyway. So I only have to worry about the external forces, and the only external force in this problem is FF. And that's my free body diagram. There's no other forces on this system. So then I can basically apply Newton's second law to the system in the x direction. So I get F_sys in the x direction is equal to the mass of the system times the acceleration of the system. So again, this is just FF, and this is just, well, we already worked this out. It's N times M, and that's A. And therefore, the only thing I don't know is A, which is just the mass of the system. Sorry, the force, rather. A is just the force, FF on the system, divided by the mass of the system, which is capital M times little m. And I've got the acceleration. So it's easy and quick to get the acceleration by treating the whole thing as a whole system as an object. So I'll write that down over here because I've got it now. A is equal to FF over capital N times M. I've done that. But now I want to figure out the individual tensions. What's my approach for that? Well, again, I don't want to write down N free body diagrams. I only want to write down one more free body diagram. But I want to find one more free body diagram to find the ith tension. So the question is, how do I define a system that gets me at the ith tension? Because if I just write down a free body diagram for one block, I have two tensions, and I've got two tensions. I want a system that's as simple as this, where there's only one force applied to the system. And it turns out that the key is to pick a new system, not the whole one, but a new system where the force that you're interested in is the force that turns out to be the only force on the system. So I have to pick a system where that force is being applied, but then I have to pick a system where no other forces are being applied. That's the tricky part. There's no algebra for doing this kind of thinking. You have to conceptually tangle with the notion of a system and say, well, suppose I want the system that the TI tension is applied to and nothing else. Well, TI is applied on this side, but it's also applied on this side. Now, this side is complicated because I've got some arbitrary number, which I'd have to kind of work out, of blocks. I don't know how many there are. In this case, there's 2, but if there's 50 blocks, I'd have to go count those blocks, and that's a mess. And then I've got an applied force, and so it gets complicated. But on this side of TI on the left, I can divide a system which is just all the blocks to the left. And the happy news is that because I set up the problem the way I have, I know how many blocks are in that system. There are I blocks. So to the left of TI, to the left of block 4, say I is 4, are 4 blocks. 1, 2, 3, 4. And if I define a system, that's the boundary of the system right there, because I'm attaching that rope to that system. That system itself, there's no other forces applied to that system in the horizontal direction except TI. These forces are internal to the system, 1, 2, and 3, and all those other forces are external. They don't touch the system. The only thing touching the system is that. So in other words, the free body diagram for the new system, this is the new system, which I'll call, M cis comma I, for the system made of the I blocks, in this case 4 blocks, looks really simple. So again, vertical forces we ignore, and then there's only one external force applied to that system, and that point of contact, every time you have a force on a system, there's a point of contact. That's the point of contact right there, where that rope comes into contact with the system. And that force is just T sub I. So I write down Newton's second law, and I charge away with this free body diagram. Again, that's X right there. So this is a really simple free body diagram. But let's write it down. F net on the system for the system made of I blocks is equal to the mass of that system. So this is, I'll call this M cis I, times the acceleration of that system, comma I. That's Newton's second law, X equals ma. Well, the only force on the system is T sub I. The mass of the system, I've got, how many blocks do I have? I have I blocks. So that's I, the number I, which in this case is 4, for example, times the number of blocks, which is m. That's the mass of the system. And the acceleration of the system, we already know what it is, right? So that's just, I substitute the result from before. That's F app over n times m. Well, things are simplifying really fast. So the tension on the block, on the ith block to the right of the ith block, basically, is equal to, well, the m's cancel, and I get the ratio I over n times Ff. Yay! Much simpler than doing 50 equations with 50 unknowns. In other words, I pick a subsystem. I pick a subsystem, which is made of I blocks, or as many blocks as you want. And the beauty of picking a system to the left is that system has only one force on it, and that's the force that I want. In other words, this is the unknown, and I can express it in terms of all these other things, which I now know. I know it because I've figured out the acceleration. Let's stare at this a little second, and let's make sure it makes sense. That's a force. That's a ratio of 2 pure numbers, and that's a force. So that's great. Notice that this answer doesn't depend on the value of the mass of the blocks. It just depends on the value of the applied force. Notice that if I pick I equals 1, then the tension on the first block is 1/nth of the applied force on the last block. And the tension on the second block is 2/nths of the applied force, and 3/nths, and 4 on, all the way up to the tension here, which is n minus 1 over m, right? So in other words, the tension grows by a fixed increment as I move to the right, growing from 1 over n times the applied force all the way to ultimately on the right-hand side to the applied force. In other words, you can think of the applied force as the force that's needed to overcome the motion of this block plus everything else, and then the force of this tension, it can be less because it's not pulling the whole train, it's only pulling the train with one less block, and so on and so forth. So each time I go to the left, the tension gets less because I need less tension to get the acceleration of that system to the left. Okay? So that's the problem with the train. Again, the key issue for these trains is if you aren't given the acceleration, I mean, how can I say, if you're given the acceleration, you're all set. You can just plug it in here and you do this expression and you're done. But if you're not given the acceleration, first you pick the whole system to figure out what the acceleration is, and then you pick a subsystem that zooms in on the forces that you want to figure out the forces anywhere you want. Once you know that acceleration, you just apply Newton's second law and it becomes simple. All right, that's it.